Hello class, welcome to our Combinatorics lecture for Monday, April 20th. So we're getting close to the end here. Next Monday, April 27th is technically that's the last class day, although that doesn't really have a lot of meaning here in our new online format. Well, anyway, so what's going to happen is we'll have today's lecture, of course, which I'm getting ready to present to you. This is more about recurrence relations, and in this case, solving recurrence relations. And then we'll have another lecture on Wednesday, April 22nd. That will be more on solving recurrence relations. And then next Monday, April 27th, that's the test day. And so the third test will be posted at the regular class time, which is 8:30, and then it will be due back to me on Wednesday, April the 29th, right? And now for some of you, as I mentioned, if once you've got your test grade back, if you are satisfied with that, the average of your 3 midterm test grades, then that can replace your final exam score, and so you do not have to take the final exam. If you do need to take the final exam, though, to improve your score, then the final exam is the following Monday, same format, right? So it would be posted on Monday, May the 4th at 8:30, and then would be returned to me on Wednesday, May the 6th, right, for grading. So we have now a sample test posted for test number 3. So that sample test is posted on the Blackboard page under the sample test link. And so that it covers inclusion, exclusion, and then recurrence relations, which we're talking about now. And then there is an optional homework 7 posted. That's just to give you more practice with recurrence relations for the test on April 27th, right? But you do not have to submit homework number 7. You do not have to turn that into me. However, if you want to turn that into me, you can. Turn that into me. That would be due Monday, April 27th as well. Oh, no, that would be due Wednesday, April 29th when you turn in your test. And then I will grade that and then use that if that will improve your homework average, right? Okay. So homework number 7 is optional just for you to just to give you more practice with recurrence relations. I'm going to on Monday then, since that's the test day, I will not just like last time. I will not give a new lecture on Monday, April 27th. So we're finished on Wednesday in terms of material. That April 22nd, this coming Wednesday, will be done in terms of material. But I will use that lecture on Monday, April 27th to go over the sample test. So, so to go over problems on the sample test, so that and then you can watch that, and that may help you when you're taking the test on Monday, April 27th, right before you return that to me. So, so this is the activities for the remainder of the semester. Right, and as usual, you can contact me during my Zoom office hours, or you can email me, or you can even call my office phone number. I think that's still being forwarded to me, so you can call me as well if you need to talk with me about something. Okay, I don't think I have any more sort of class announcements that I need to make. The well, so I'm hoping everyone is doing okay. It seems like most everyone is participating. You've been, you returned your test, and you've been submitting your homework, so that's good. So just one more homework assignment to submit, and that's homework number 6, and then take the test, right? And so then we'll hopefully you will not need to take the final exam, and so you will be finished, right? All right, so let's go ahead and get started with the notes for today. before I burn up too much more time just blabbering here. And so today we're talking about, as I mentioned, solving recurrence relations. So last time we took a look at setting up recurrence relations to count certain types of sets, right? But solving recurrence relations means taking the recurrence relation and converting it to a non-recurrent formula, right? To a formula that doesn't involve recurrence. And we just saw one example of doing that. Last time we did it sort of by trial and error, by substitution in the recurrence relation. But today we're going to learn some more systematic ways of solving recurrence relations. But before we get to that, I want to do one more example of setting up a recurrence relation. There are lots of, this is a very typical example in the, you'll see on the sample test and in the homework, so I wanted to give you a little more practice with setting up recurrence relations. Okay, so first we want to find a recurrence relation for the number of bit strings, that is, sequences of bits, right? Bits are zeros and ones. So the number of bit strings, we're going to call that S sub n, and so these bit strings will have length n, but we want our bit strings to not contain this sequence, 0, 0, 1. So we want to see how many bit strings we have of length n that do not contain 0, 0, 1, right? And we'll call that number S sub n. So it's kind of obvious here that S sub 1 is equal to 2, right? Because you've only got two bit strings of length 1. One of those is 0, right? And the other one is 1. And obviously none of those, neither of those is going to contain 0, 0, 1, right? Because it's not long enough. So S sub 1 would be equal to 2. Both of these count, right? And S sub 2, for the same reason, S sub 2 is going to be equal to 4 because obviously bit strings of length 2 cannot contain these 3 bits, right? And you've got 4 bit strings of length 2, correct? Those are the 4, right? So all 4 of those would count, and so S sub 2 is equal to 4. And we could also count S sub 3 probably just by inspection. Maybe even S sub 4 we could count by inspection, right? But now let's go ahead and develop this recurrence relation, right, S sub n, that we can use to count this number of bit strings we're interested in for any length, right, n. All right, so here's the way we're going to think about this. Suppose that we have a bit string of length n here, right? Okay, so n's just an arbitrary number. So when we're creating a bit string of length n, right, we have to fill in n bits, right? So we got to put in zeros and ones into each of these slots, right? But if we start with the first slot, of course, right, then we've only got a couple of choices, and one of them would be 1, right? So let's just imagine that we put a 1 in the first slot, right, in our bit string of length n. Then, since we don't want the bit string to contain 0, 0, 1, right, that means then that the rest of the string cannot contain 0, 0, 1, right? Okay, so these n minus 1 bits that are left over when you fill in a 1 in the first position, those n minus 1 bits cannot contain 0 at 0, 1. So how many bit strings of length n minus 1 do not contain 0, 0, 1? Well, by definition, that would be S sub n minus 1, right? So see, we already know here that S sub n, bit strings of length n that don't contain 0, 0, 1, right? That includes at least bit strings of length n minus 1 that don't contain 0, 0, 1, right? Because if you have a bit string of length n minus 1 that doesn't contain 0, 0, 1, you can fill that into these slots and then put a 1 at the beginning here, and you would have a bit string of length n, right, that doesn't contain 0, 0, 1. So we know S sub n has at least S sub n minus 1 many bit strings in it, correct? Now, but it may have more, right? Okay, because we don't have to begin our bit string with 1. So suppose again now we've got the n bits, right? But instead of starting with 1, right, suppose we start with our other choice, which is 0. Okay. All right. Now that's a little bit harder to analyze than if we began with. That's a little bit harder to analyze than if we begin with 1. All right. So if we're going to begin with 0, we have to think carefully about what we put in the second slot. All right. Well, in the second slot, right? You've only got 2 choices, correct? So one of those is a 1, right? Well, if you put a 1 in there, right, then, right, okay, that means these first 2 bits, right, do not begin a 0, 0, 1, right, okay, because you start with a 0, 1. Then you know, those are not contained in a 0, 0, 1, right? So if you begin with 0, 1, then what you've got are these remaining n minus 2 bits, right? And you know that these cannot have a 0, 0, 1 in them, right? Okay, because these two sort of don't count any longer. All right, so, well, how many bit strings of length n minus 2 do not contain 0, 0, 1? Well, the answer is, by definition, s sub n minus 2, correct, right? Okay, because that's how we're labeling bit strings that, of a particular length that don't contain 0, 0, 1. Oh, so now I know s sub n is at least as large as s sub n minus 1 plus s sub n minus 2, right? Because how do we get the s sub n minus 2? Take any bit string of length n minus 2 that doesn't contain 0, 0, 1, right? Put it here and then add a 0, 1 in these 2 bits, and you would have a bit string of length n that doesn't contain 0, 0, 1. All right, so that's why this term we would add. Now, however, what's the other possibility, right? Okay, well, you could start with 0, and instead of having a 1 here, you could have 0 here. Now, notice if you have a 0 here, then things get kind of fixed from that point on, because if you have 2 zeros to start with, what can you put in the third position? You cannot put a 1, because then you would have 0, 0, 1, right? So the third position must be a 0. But if you've got a 0 in the third position, then the fourth position must also be a 0, because if you put a 1 here, you will still have 0, 0, 1, right? And you use that same logic all the way down. So actually, if the string begins with 2 zeros, it's going to have nothing but zeros in it. So if your string begins with 2 zeros, you only got one possibility for a bit string that doesn't contain 0, 0, 1. That's all zeros. Oh, so I would add over here then just an extra 1. Oh, there it is. See, there's the recurrence relation. How many bit strings of length n do not have 0, 0, 1 in them? Well, it would be the number of bit strings of length n minus 1 that don't have 0, 0, 1, plus the number of bit strings of length n minus 2 that don't have 0, 0, 1, plus you get this additional 1, the bit string that has all zeros in it. So let's use that then to count some bit strings here just for fun. So how many bit strings of length 3 don't have 0, 0, 1? Well, let's see. What does this say? It says you take s sub n minus 1, that's s sub 2, right? Plus s sub n minus 2, which is s1 here, and then you add on an extra 1. So that gives us what? 4 plus 2, right, plus 1 equals 7. That's the correct answer, right? Because if you have a bit string of length 3 and it doesn't contain 0, 0, 1, well, that means you have every other option except for 0, 0, 1. Well, there are 8 bit strings of length 3, and this is the only one that has 0, 0, 1 in it. So if you take that out, you get 8 minus 1, which is 7. So see, this is correct, right? Okay, just from observation. S sub 4 then would be S sub 3 plus S sub 2 plus 1. And so that's 7 plus 4 plus 1 turns out to be 12. So apparently there are 12 bit strings of length 4 that do not contain 0, 0, 1, right? And so forth, right? We can continue to use this recurrence relation to count as high as we want, right? This number of bit strings. Ooh, all right, so cool, right? All right. Now let's consider. So that's just another example of creating of using a little bit of logic there to create a recurrence relation to count a particular set. Now, let's go back to this problem of once we have formulated a recurrence relation, can we convert that to a non-recursive formula, right? Okay, can we write down a formula for S sub n that doesn't rely on recursion? And now I'm going to show you how to do that. All right, so, but we have to introduce a little bit of terminology here before we get to that that method. All right, so let's go back and think about that recurrence relation that we just wrote down. S sub n equal S sub n minus 1 plus S sub n minus 2 plus 1, right? So what I'm going to do is I'm going to rewrite this equation a little bit. I'm going to take the recurrent terms, right, the recursive terms, I mean, and I'm going to pull them back over to the left-hand side. So I'm going to write this as S sub n minus S sub n minus 1 minus S sub n minus 2 equals, and then I'm going to leave the 1 on the other side, on the right-hand side. Okay. So look, in this equation, all the recursive terms are only raised to the first power. You don't have S sub n squared, right? Or you don't have S sub n minus 1 squared, or you don't have S sub n minus 2 raised to the third power, for instance. All these recursive terms are just raised to the first power. If that's the case, then the recurrence relation is said to be linear. So this is a linear recurrence relation. All the recursive terms are only raised to the first power. All right, now, another thing that we're going to look for here is what is on the right-hand side of this equation once we move all the recursive terms to the left-hand side. In this case, notice you get something other than 0. You get a 1 in this on the right-hand side of this equation. So if you get a 1 or anything other than 0 on the right-hand side of the equation, once you move all the recursive terms to the left-hand side, then the recurrence relation is said to be non-homogeneous. Okay, there's a big term. All right, non-homogeneous. If the right-hand side is 0, the recurrence relation is said to be homogeneous. All right, so non-homogeneous is not 0. 0 is homogeneous. So already we can see that that recurrence relation is linear and it's non-homogeneous because this right-hand side is not 0. Okay, if that were 0, then it would be homogeneous. All right, now here's the next thing that I'm going to do. All right, what we're going to do is look at the again the left-hand side of that equation we wrote down that has the recurrence, right? Okay, it has the recursive terms in it. What I'm going to do is I'm going to take the coefficients off of the, off of the recursive terms, okay, and I'm going to convert that into a polynomial. All right, so but I'm going to set the I'm going to set, okay, let me say this right here. Okay, I'm going to take the coefficients off of the recursive terms, okay, and I'm going to use those coefficients to create a polynomial, and I'm going to take that polynomial and I'm going to set it to 0. I'm not going to set it to whatever is on the right-hand side of the recurrence relation. I'm going to automatically set that polynomial to 0. That equation is called the characteristic equation for the recurrence relation. All right, so let me show you how I do that, right? So here was my recurrence relation, right? When I took the recursive terms and moved them to the left-hand side, right? So on the left-hand side, what were the coefficients? It was 1, -1, and -1, correct? So in order, I'm going to use those to create a polynomial. So my polynomial would be 1 times x squared, coefficient here, and then -1 times x, right? This coefficient is -1. So -1 times x, and then -1 times, well, x to the 0th power, right, which is just 1. So this third term turns out to be -1. And then I'm going to set that not to 1, but I'm automatically going to set that to 0. that equation, which in this case turns out to be a quadratic equation, right? That is called the characteristic equation for the recurrence relation. Now, it turns out this characteristic equation obviously turns out to be useful to me for various reasons, so that's why I'm creating it. But so you might be wondering, why am I going through this weird process of creating this characteristic equation? And the answer is because I'm going to use that characteristic equation actually in a moment here to help me solve the recurrence relation. So the characteristic equation for this recurrence relation, right, is x squared minus x minus 1 equals 0. Not equal 1, but equal 0. Okay? All right, so always set the characteristic equation to 0. Now, this is a polynomial equation, right? So it may have solutions. The solutions are called the roots of the recurrence relation, or sometimes called the characteristic roots of the recurrence relation. All right, now, if you take this equation, x squared minus x minus 1 equals 0, and you solve it for x, it doesn't factor, so you'll have to use the quadratic formula. But if you use the quadratic formula, you'll get two solutions to this equation. I'm going to label them r sub 1 and r sub 2. So I got these through the quadratic formula. All right, so one solution to this equation is 1 plus square root of 5 over 2, and the second one is just the conjugate here, 1 minus square root of 5 over 2. Okay, and again, those are referred to as the characteristic roots of the recurrence relation, right? So this is the characteristic equation for the recurrence relation. The solutions to the characteristic equation are called the characteristic roots of the recurrence relation. And again, I'm going to use those roots to help me solve the recurrence relation in a moment. That's why I'm going through all of this process here. Finally, one more piece of terminology, okay, almost done. Of course, polynomial equations have degrees, right? And so the degree of the characteristic equation for a recurrence relation is going to be called the order of the recurrence relation, not the degree of the recurrence relation, although it would be a crime to use that terminology. But the degree of the characteristic equation for a recurrence relation, that's called the order of the recurrence relation. So this, notice that, of course, this characteristic equation has degree 2, right? See, this is a polynomial. It has degree 2, right? It's a quadratic polynomial. So that means then that this recurrence relation is second order, or has order 2, okay? Because its characteristic equation has degree 2. You could say that the recurrence relation also has degree 2. That's okay. People will understand what you mean, right? But the real official quote-unquote terminology is order. All right. So as I just mentioned, right, this recurrence relation is second order. All right. Okay. So we're only going to be looking at second order or first order recurrence relations. So we're not going to look at higher order recurrence relations, although they do exist. All right, so here's the theorem that's very useful to us, and I'm going to give you a proof of the theorem, and so because I want you to understand a little bit about how it works, right? But once you understand, once you have applied the theorem, you're going to see it's very easy to apply. So it's a really nice theorem to use in practice. All right, so suppose that we are given a second order linear homogeneous recurrence relation. Okay, so it's got to be second order, it's got to be linear, and it has to be homogeneous, right? So that's important. And so a second order linear homogeneous recurrence relation is going to look like this. They all will have this form. So you'll have Sn is equal to something times S sub n minus 1. This coefficient can vary, and then plus something times S sub n minus 2. So this coefficient B can also vary as well. All right. but you're not going to have any other term here other than s sub n minus 1 and s sub n minus 2. You're not going to have any other terms added on. Otherwise, you would not get a homogeneous recurrence relation, right? Okay, so all second order linear homogeneous recurrence relations have this format. Now, what's the characteristic equation for this recurrence relation? Well, if you take these two terms and move them to the to the left-hand side, right, you get s sub n minus a sub n minus 1 minus b sub n minus 2, right, equals 0. So the characteristic equation then, just peel off those coefficients and of the recursive terms and turn them into a polynomial, you'll get x squared minus ax minus b, and then, of course, set that equal to 0, because you always set the characteristic equation equal to 0, right? So you get a characteristic equation that looks like this. Just a very standard quadratic equation, actually, right? Except, by the way, notice the leading coefficient is always going to be 1. All right, so of course you can take that quadratic equation and you can solve it, right? Okay, and it may have no solutions. That would be unfortunate, but it may have 2 solutions, or it may have 1 solution, right? Okay, and so we're going to break that up into 2 cases. Suppose the characteristic equation has 2 solutions, all right, R1 and R2. So these are the roots, right, of the recurrence relation, right, because those are the solutions to the characteristic equation. Then guess what? Here is the solution to the recurrence relation. It's very easy to write down the solution to the recurrence relation. It's just going to be s sub n is equal to some constant. This is not a, okay? So some constant that I'm calling C1 times, notice it's the first root, right, to the nth power, plus a second constant C2 plus the second root to the nth power. Now, you may be wondering, well, how do I determine what these 2 constants are? That is determined by the initial conditions that you were given for your recurrence relation, right? That depends on what small values for the recurrence relation you were given. So if you can use those small values for the recurrence relation to determine the correct value for C1 and the correct value for C2, okay? But in general, these constants could be anything, right? So notice the form of the solution to the recurrence relation. Some constant times the first characteristic root, right, to the nth power, plus some constant times the second characteristic root to the nth power. This is not recursive, right? This is not a recursive formula. So, so that's going to be, I claim here, the solution to the recurrence relation. Just that simple. So if you can solve a quadratic equation, that's really cool. If you can solve a quadratic equation, you can solve a, and that we certainly know how to do, right? That means you can solve a second order linear homogeneous recurrence relation, okay? All you need to be able to do is solve quadratic equations. Wow, quadratic equations are really useful, aren't they? All right, now it is possible, of course, that your characteristic equation will only have 1 solution. And if that's the case, then the solution to the recurrence relation is really also easy. It's going to be C1 times your 1 single solution, right, to the nth power, plus C2 times, notice you have to throw in this factor of n, okay, times, again, your 1 solution to the characteristic equation to the nth power, right? See, you don't have 2 different solutions to the characteristic equation if you've only got 1 solution to the characteristic equation. Then you have to you still have 2 terms in your solution to your recurrence relation. One of them is going to be, again, constant times your root to the nth power, plus the second term is going to be constant times this factor n thrown in, right, times your root to the nth power. So very similar to this, right, except this extra factor of n you have to put into the second term. And again, as I mentioned earlier, the constants C1 and C2, how are they determined? They're determined by the initial conditions given for the recurrence relation. Okay, I have a proof, so I'm going to show you the proof of a part A of this theorem. Part B uses very similar logic, so if you've seen part A, you don't need to see part B. It's going to work almost exactly the same way. Before we actually prove part A of this theorem, so show you why this is true, then, but let's use it, because you look at it, it looks kind of all very abstract, right? So let's actually apply it in a specific case, and you can see how easy it makes solving recurrence relations. So let me skip through all of my proof here, and let's get to an actual nice example here. All right, so suppose we've got this recurrence relation. This is just kind of a made-up recurrence relation. S sub n is 2 times S sub n minus 1 plus 3 S sub n minus 2, right? And we're given that S sub 0, so these are the initial conditions. This is what I mean by initial conditions, right? These are small values for the recurrence relations, right? So we're given that S sub 0 is equal to 0 and S sub 1 is equal to 8. All right, so S sub 0 is 0. And S sub 1 is equal to 8. And then, now, of course, you can use the recurrence relation, right, to determine what S sub 2 is. So S sub 2 would be, according to the recurrence relation, right, it's 2 times S sub 1, because 2 minus 1 is 1, right? So 2 times 8 plus 3 times S0, right, because we're looking for S sub 2. 2 minus 2 is 0, so S sub 0 times 3. But S sub 0 is 0, so we just get 16, right? Or, what would S sub 3 be? That's 3 times S sub 2, right? But S sub 2 was 16, plus 3 times S sub 1, but S sub 1 is 8. Well, this is already getting big. So we have what? 48 plus 16 is 64, okay? And then, of course, you can continue, right, generating more values for the recurrence relation, right, using this formula. But what I want to do is turn this recurrence relation into a non-recursive formula, and that's what the theorem helps me to do, right? Okay, so what do I need to write down the non-recursive formula for this recurrence relation? Well, we need to write down the characteristic equation, right? So remember, take your recurrence relation and set it equal to, well, we're hoping we'll set it equal to 0, right? Because if we don't, you're not going to have a homogeneous recurrence relation, right, which is what we need for the theorem. So when I said set it equal to 0, what do I mean? Take these two terms, right, and so the two recursive terms, pull them back over to the left. So you would get S sub n minus 2 times S sub n minus 1 minus 3, S sub n minus 2, right, equals, notice there's nothing left on the right-hand side now when you move these two terms to the left. So it's equal to 0. That's perfect. That means then that this recurrence relation is homogeneous, right, okay, because when we move the recursive terms to the left, the right-hand side turns out to be 0. Nice, okay, so it's homogeneous, it's linear, right, because all of the recursive terms are just raised to the first power, right, so linear, homogeneous, it's second order, because what is the characteristic equation for this recurrence relation? It's going to be x squared, that corresponds to S sub n, minus 2 times x, that corresponds to the S sub n minus 1 term, right, minus 3, because that corresponds to the S sub n minus 2 term, right, equals 0. So there is the characteristic equation for the recurrence relation. And now we want to find the roots for the characteristic equation. Those are the characteristic roots of the recurrence relation. So hopefully I don't have to use the quadratic formula to solve this, and I don't, because this one is going to factor nicely, right? So this factors as x minus 3 times x plus 1. So our two solutions are 3 and minus 1. And now, once you've got those two solutions, you're really essentially home free, right? You know that S sub n then is going to be what? Some constant times what? That first root, right, to the um, nth power, correct? And then plus, right, your second constant, right, times the second root, right, to the nth power. That's it, okay? That's all there is to it. See, that's so simple. There's just the general solution to the recurrence relation. This is a non-recursive formula, right? Now, what are the C1 and C2, right? What are these two constants? Well, we have to adjust those, right, to meet the initial conditions, right? Here are the initial conditions. So I have to pick C1 and C2, right, so that they will match my initial conditions. All right, so how do I do that? Well, I'm going to do that by substitution, right? Okay, because S sub 0, right, is supposed to be 0, but it's supposed to, S sub 0 is also supposed to match this formula. So 0 should be C1 times 3 raised to the 0th power. See, the subscript here is 0, right? Okay, this value 0 came from my initial condition, right? And now plus C2 times minus 1 raised to the 0th power. So what does that work out to be? That says 0 is equal to, of course, raising these constants to the 0th power gives me 1, right? So I have 0 is equal to C1 plus C2, right? Which I guess means that, how do we want to write this? Okay, I guess that means C2 is equal to minus C1, right? All right, now second initial condition. So we know S sub 1 is equal to 8, but that is equal to C1 times 3 to the first power plus minus 1, oops, I forgot the C2, right? Plus C2 times minus 1 to the first power. So I get what? 8 is equal to 3C1 minus C2, right? But C2 is minus C1, so now I'm in business here, right? This is 3C1 minus a minus C1, right? Because C2 is negative C1. So it looks like 4C1 is equal to 8, which tells me, right, that tells me that C1 is equal to 2. Am I doing that right? 8 is equal to 4C1, so C1 is equal to 2, and C2 is minus C1 according to this equation, right? So it looks like C2 would be minus 2. So there are your initial conditions, right? So let's see. So now we know that S sub n is 2 times 3 to the nth power plus, and now we have negative 2, so I guess I should write just minus here, minus 2 minus 1 to the nth power, right? C2 is negative 2, so minus 2 times minus 1 to the nth power. Let's see, does that give me the right value for S3 that I thought I was supposed to get, which is what, 64, correct? Does this give me 64? It doesn't look like it. Let's see, so I have 2 times 3, cubed, right? 2 times 3 cubed minus 2 times minus 1 cubed. So let's see, this looks like 3 cubed is 27, 2 times 27 is 54, and this looks like plus 2 is 56. Whoops, is that what okay, so I'm off somewhere. Where did I get off here? Right, so because I was expecting there 64. All right, so let's see. So S sub 2 is 2 times S sub 1 plus 3 times, so that is 16. Oh, I see what I did wrong. This was supposed to be 2, right? Okay. So S sub 3 is 2 times S sub 2. So that's 2 times 16 plus 3 times S sub 1. But S sub 1 is 8. Oh, so this is 32. Let's see. So what do I have here? 32, right? Well, I was totally off on this, right? So this is 32 plus 24, right? 2 times 16 is 32, 3 times 8 is 24, which indeed is 56. Okay, so I'm terrible with my terrible there with my recursive arithmetic, right? It's a good thing I had this non-recursive formula, right? Now they agree, correct? Okay, because I did this, because I did my recursion wrong up here a moment ago. Okay, all right. So see, there's the process of solving a linear second order, right? Linear second order homogeneous recurrence relation. Okay, let's pause here for a moment, and because I want to show you the proof of this nice result, right? So the proof of this theorem, and then we'll look at a couple more examples again of applying the theorem. All right, so I'm going to pause here for just a second. Okay, we're back. Before I show you the proof of our theorem, the main theorem that we're using today, let me give you a second example, though, of actually applying the theorem. Okay, so here we have here we have this recurrence relation. S sub n is equal to 4 times S sub n minus 1 minus 4 times S sub n minus 2, right? So it looks like a fairly straightforward, right, recurrence relation. And again, if we take the recursive terms, right, and pull them over to the left-hand side with S sub n, we will get an equation that looks like this. And so that means we have a homogeneous recurrence relation, right, because this right-hand side of that equation turns out to be 0, right? When you take these two terms, pull them back to the left, the right-hand side ends up staying 0. So this is a homogeneous recurrence relation because this side is 0. And it's linear because our recursive terms are all raised to the first power only, right? And it's going to be also second order because if I write down the characteristic equation for this recurrence relation, that turns out to be a degree 2 polynomial equation, right? It has degree 2. So this is second order linear homogeneous recurrence relation, exactly the type that our theorem allows us to solve, right? Okay, so now to solve, I need to have the solutions to the characteristic equation correct. And so again, this characteristic equation is very easy to solve because it factors. So we get x minus 2 times x minus 2 equals 0. And that means you have just one characteristic root, right? 2 is the characteristic root. So with only one characteristic root, right, that means then that we have to slightly adjust our solution to our recurrence relation, right? Okay, so we're going to write S sub n is equal to, again, some arbitrary constant times this root, this characteristic root raised to the nth power, plus, again, c sub 2, an arbitrary constant times this same root to the nth power, but you must throw in this extra factor of n in this second term. Okay, so the general solution to our recurrence relation looks like c1 2 to the nth power plus c2 times n times 2 to the nth power, right? And now again, to find the specific values for c1 and c2 we need in this instance, that depends on these two initial conditions, right? So we're going to use these initial conditions to find c1 and c2. All right, so we know that s sub 0 is supposed to be 1. S sub 0 would be C1 times 2 to the 0th power plus C2 times 0 times 2 to the 0th power, right? Okay. But, wow, what is that? That looks like just C1, correct? All of this just reduces to C1. This term is 0, so you get C1 times 2 to the 0th power, but that's C1 times 1. So you just get S sub 0 is equal to C1, but our initial condition says S sub 0 is supposed to be 1. So now we know that C1 very easily is equal to 1. Ooh, that was nice, right? And now what about S1, right? That is going to be C1 times 2 to the first power plus C2 times 1 times 2 to the first power, correct? But that's supposed to turn out to be also 1 according to our initial condition. So it looks like I have 2C1. This is going to be 2C1 plus what? 2 times C2 is equal to 1. But C1 we already discovered was 2. So I have 2 plus 2C2 is equal to 1. So it looks like 2C2 is minus 1, or very nicely here, C2 is equal to minus 1/2. So those are going to be, right, the specific values for C1 and C2, right, that will match these particular initial conditions. So the correct solution for my recurrence relation is what? 1 times 2 to the nth power minus 1/2 times n times 2 to the nth power. Nice. Let's see if that gives us some correct values for this recurrence relation. So let me compute some, if I can do it properly this time. So S sub 1 is equal to 1. S sub 0 is equal to 1. S sub 1 is equal to 1. And now we have S sub 2 is equal to what? 4 times S sub 1. So 4 times 1 minus 4 times S sub 0. But S sub 0 is also 1, so it looks like S sub 2 is 0, right? What about S sub 3? That's going to be 4 times S sub 2, which is 0, minus 4 times S sub 1, which is 1. So that turns out to be 4. What about S sub 4? S sub 4 is going to be 4 times S sub 3, which is also 4, right? Minus 4 times S sub 2, which is 0, so that looks like 16. Does that does S sub 4 match our recurrence relation here? Let's see. Does S sub 4 16, does that match our non-recursive formula? According to our non-recursive formula, right? S sub 4 should be 1 times 2 to the 4th power, right, minus 1/2 times 4 times 2 to the 4th power again. Does that match? Doesn't look like it matches to me here, right? Have I miscomputed the recursion again? 2 to the 4th power is 16 minus, and this is going to be 2 times 2 to the 4th power. So that's 2 to the 5th power, which is 32, which comes out to be minus 16. So what did I miscompute up here? Oh, I know. This S sub 3 was supposed to be minus 4, right? So we have here 4 times a minus 4, minus 4 times 0, which indeed is minus 16. Okay, so they do match. All right. So again, I messed up computing S sub 4 recursively, but I got it right computing it non-recursively, right? Okay. Okay. All right. So there's two examples at least, right, of converting recursive recurrence relations to non-recursive formulas. All right. Okay, so let me show you one last example, and then we'll have to save the proof for Wednesday, which is fine. So I want to come back and look at this example. This is one that we have already done. I mean, this is a recurrence relation that we've already looked at, but we haven't solved the recurrence relation yet. So I want to show you how to solve this recurrence relation that we had already looked at. So b sub n equal b sub n minus 1 plus b sub n minus 2, and with these initial conditions, b sub 1 is 2 and b sub 2 is 3. This recurrence relation counts the number of bit strings of length n that do not contain 0, 0. So we had this in the notes for last time, developing this recurrence relation, and so I want to use it again and solve it, okay? Because this is a second order linear a homogeneous recurrence relation. It's actually a Fibonacci recurrence relation, okay? And so I want to talk about how we can convert that to a non-recursive formula. All right, so when you write down the characteristic equation for this recurrence relation, you get x squared minus x minus 1 equal 0. All right, so you can try that. And you get this characteristic equation, x squared minus x minus 1 equals 0. And that does have solutions. You can find them using the quadratic formula. So the two solutions, the two characteristic roots, turn out to be r sub 1 is 1 plus the square root of 5 over 2, and r sub 2 is 1 minus the square root of 5 over 2. So not pretty roots for the characteristic equation, but there they are. There are two of them. Legitimate real number solutions, 1 plus square root of 5 over 2 and 1 minus square root of 5 over 2. Okay, so that tells us that by our theorem, here is what our non-recursive version of our recurrence relation looks like. So it's going to be S sub n is equal to, again, some constant c1 times our first root, 1 plus square root of 5 over 2 raised to the nth power, plus some constant c sub 2 times our second root, 1 minus the square root of 5 over 2 raised to the nth power, right? So there is this very awkward, right, solution to our recurrence relation. Now, we need to figure out what C1 and C2 are, okay, to match our initial conditions. Remember, the initial conditions, I think, were B1 equals 2 and B2 equals 3. So what I'm going to do is, this is supposed to be B, actually, not S. All right, so what I'm going to do now is fill in, right, B sub 1 equal 2 and B sub 2 equal 3 into this formula, right? So I'm going to put in 2 for B sub 1 over here on the left-hand side of this equation, and then the n is 1, right? So I'm going to put 1 in for the exponent here on the right-hand side of this equation, and that gives you then this formula, all right, this equation. 2 is equal to c sub 1 times our first root to the first power plus c sub 2 times our second root to the first power, okay? Now I'm going to do the same thing with b sub 2, right? So b sub 2 is equal 3, so I'm going to put 3 in to the left-hand side of this equation, and then I'm going to plug 2 in for n into the right-hand side of the equation. And so I've got these two equations now, and I have to solve them simultaneously for C1 and C2. Ooh, that's not easy to do, right? Okay, kind of a mess here, correct? Right, to solve these two equations for C1 and C2. All right, I didn't attempt to do this by hand. I let Wolfram Alpha solve these two equations simultaneously for me for C1 and C2, and Wolfram didn't think about it very long. Okay, here are these two constants, C1 and C2. So C1 turns out to be 1/10 times 5 plus 3 times the square root of 5, and C2 turns out to be very similar. It's 1/10 times 5 minus 3 times the square root of 5. Do you believe that? Well, we'll have to trust Wolfram Alpha, right? Or you can try to solve that yourself. Solve these two equations simultaneously for C1 and C2. Anyway, this is what we get. So if you plug those back in then to our recurrence relation, again, this is supposed to be b sub n. All right, here's what we get. We get b sub n is equal to this. Okay, there's c1 times, again, our root raised to the nth power, our first root raised to the nth power, and then here's c sub 2 times our second root raised to the nth power. There it is. Kind of ugly, right? But so the original recurrence relation is much prettier, right? The non-recursive solution is really kind of ugly there, right? Now, if you use the recurrence relation, you can see from the recurrence relation kind of easy that b sub 3 is b sub 2 plus b sub 1, and so that turns out to be 3 plus 2, which is 5. Okay, so b sub 3 is 5. That means there must be 5 bit strings of length 3 that do not contain 0, 0 in them. All right, so it's easy to compute b sub 3 from the recurrence relation, right? This is supposed to be so b sub 3 is supposed to be b sub 2, which we knew was 3, plus a b sub 1, which we knew to be 2. Okay, so b sub 3 is 3 plus 2, which is 5. That's not so easy to get out of the formula, though, right? Okay, to compute b sub 3, right, using the formula, you would have to plug 3 in here for n into this formula, and then do these, simplify all of this arithmetic, right? Plug 3 in for n, cube those roots, right, and then multiply all of this out. But lo and behold, that's supposed to turn out to be 5, okay? Wow. Okay, it's kind of amazing that it turns out to be a whole number, right? But it does. When you plug 3 in for n and do the calculations, you will get 5. Okay. So in this case, actually, I think the recursive version of the recurrence relation, right, is much easier to use than the non-recursive version, right? Because the arithmetic here is kind of messy, right? All right. Well, so there is a technique for solving, again, linear second-order homogeneous recurrence relation. But fortunately, a lot of the recurrence relations that we encounter in practice are linear second-order and homogeneous, like Fibonacci recurrence relations, because they occur very frequently, right? This is an example of a Fibonacci recurrence relation, and so we are able to write down a non-recursive version of this recurrence relation. Now, if we think all the way back to the beginning of the lecture, right, seems a long time ago now, right, remember the recurrence relation that we developed for counting, what was it? It was the number of bit strings that do not contain 0, 0, 1, right? The number of bit strings of length n that do not contain 0, 0, 1. Here is that recurrence relation. Notice this is non-homogeneous, though, okay, because of this extra 1 thrown in. So we're not going to be able to solve this recurrence relation, unfortunately, using the theorem that we learned today, because the recurrence relation is non-homogeneous because of this little darn plus 1, right, messes things up. All right, so next time we're going to learn how to solve a non-homogeneous second-order linear recurrence relations. Okay, there's really it's just a little bit more complicated than solving homogeneous second-order linear recurrence relations, and then we'll be able to see what the non-recursive version of this recurrence relation is. All right, okay, so, well, we're done for today, right? So I think I said everything I needed to say about tests and homework and so forth at the beginning of the lecture. So I will see you again on Wednesday. Remember, the sample test is for number 3 is already posted, so I will see you again on Wednesday. Stay safe, right? Usual advice, wash your hands. Be sure to wear a mask now when you're outside with people, in a group of people, because I've been looking at some of the research about mask wearing, and so I'm kind of convinced that it actually is moderately helpful. All right, so so wear a mask. All right, all right. I know it's a little bit awkward, but do it anyway. All right, so I will see you again on Wednesday. Take care until then.